Welcome everybody in AP Chemistry series. Today we'll start with section 7.7. But before we start, we have to recall some points that were covered in the previous videos. So first of all, if I ask you to write the Kc expression and the Kp for sure for this reaction, the first thing that you have to keep in mind is checking the states of all of these reactants and products. So since they're gaseous, then they're accepted in the expressions of Kc and Kp. So as we learned, the Kc represents the ratio or the concentration of the products over to the concentration of reactants, and keep in mind A is multiplied by 2, the coefficient is 2, then it's raised to the power 2 and it's multiplied by reactant B. And the same thing is repeated with Kp, but I have to use a partial pressure for all of these species. So we have to say the pressure of a species C over the pressure of a species A to the power 2, and it's multiplied by the pressure, partial pressure for sure, of B. And the only thing that you have to keep in mind, the values that we put inside, like the concentrations or the pressures, must be at equilibrium. So we're talking about equilibrium concentrations. The question, how can I calculate the value of Kc and Kp if you were given initial concentrations instead of equilibrium? How can I do that? So let's start with the first example. The question says if the Kp for the following reaction is 2.4 times 10 to the power negative 9, and the initial partial pressure of CO2 is 2 atmospheric, what are the partial pressures of substances at equilibrium? So the first rule says we're going to apply something called Rice table. And actually it represents reaction. It represents reaction, initial change, and equilibrium. It's a long word, I don't like to write it. As we said, we're going to use reaction. So this is our reaction. At initial time, according to the equation, the only piece of information that is given to us is the partial pressure of CO2. So you can see the partial pressure for CO2 was 2 atmospheric pressure. And since we have a solid species, we don't care about it. And, like the expression of Kc's and Kp's do not include solids in their calculations or expressions. So we don't care about them. At initial time, since we have only CO2, there will be no pressure of carbon monoxide, CO, so it's going to be 0. And since we're dealing with reactant versus product, we're supposed to have a decrease in the pressure of reactant and increase in the pressure of a product, because like the reactants are consumed and the products are produced. So the change in here is going to be like minus x, because like we'll be decreasing the pressure in here by a magnitude of x. But why it's x only? We don't know actually the loss of a pressure at that point. We have only 1 mole of CO2. You can see it's not multiplied with anything. You can see it's 1 here. So it's going to be minus 1x, and that's why it's represented in that form. If you come back again to the CO in here, it's a product, its pressure will be increased. That's why we have to say positive. But since it's multiplied by number 2, or the coefficient is 2, then I have to say it's 2x. At equilibrium, since we are dealing with R, initial change, and equilibrium, we will subtract this x from this one in here. So it's going to be 2 minus x. This is at equilibrium. And here it's going to be 0 plus 2x. And since 0 plus 2x actually at the end is equal to 2x in here. The question is asking me what's going to be the partial pressures of the substances. I need to calculate the partial pressure of CO and the partial pressure of CO2. Kp is equal to the partial pressure of CO to the power 2 over the partial pressure of CO2. Okay, and since the Kp actually value is given to us, it's 2.4 times 10 to the power negative 9. You can notice that this value is very small. So since the value is very small and actually it's less than 1 times 10 to the power negative 4, we can make so many approximations. So how can I do this approximation in order to make solutions easier? I wrote the value of Kp and it equals to the partial pressure of CO2, but it's at equilibrium. So what I care about is this magnitude in here. Okay, so I have to say it's 2x to the power 2, according to the Casey, it's multiplied by 2 in here, so I have to put 2, and it's over um, 2 minus x, and that's it. But we have a beautiful approximation at that point. It says if the value of Kc or Kp is less than 1 times 10 to the power negative 4, and since ours is 10 to the power negative 9, we can neglect the value of x in here because it's going to be so small. Keep in mind we neglect this one here, but not this one here because my target is to calculate the value of x. If you neglect this one, you will have no equation for sure. So we neglect the value that comes with numbers like this, like plus or minus something. 2.4 times 10 to the power negative 9 and equals 2. 2x squared equals 4x squared over, we neglect the value of x, so it's going to be 2. All right, and now if you do some math, you can make a cross multiplication, and you can say 2 times 2.4 times 10 to the power negative 9 is equal to 4x squared. You divide it by 4, divided by 4, 1.2 times 10 to the power negative 9, and if you take the square root for both, then x is going to be 3.5 times 10 to the power negative 5. Okay, but we didn't finish, okay? We calculate the value of x, right? But my target is to calculate the value of 2x and the value of x in here. Okay, so I just want to erase the stuff in here and rewrite the things that we wrote before. And here at equilibrium, it's 2 minus x, it's plus 2x. Since we determined the value of x right here, I can calculate the partial pressure for CO, which is 2x. I can say, okay, 2 times the value of x, which is 3.5 times 10 to the power negative 5. The answer is going to be 6.92 10 to the power negative 5. And what about the value in here? If you apply it here, you can say like it's 2 minus x. The value of x actually represents 3.5 times 10 to the power negative 5. We can see that's very small value, and it's almost 2. So the answer is going to be 1.99999 stuff. And actually, it's almost 2. As we can see, we have 3 species: products and reactants with their given corresponding amounts in the reaction in here. So we have 9.22 moles of A, 10.11 moles of B, and 27.83 moles of C. So first of all, this is going to be R, like this is the reaction. At initial time, the amount of A was 9.22, and for B, it was 10.11, and for C, it was 27.83. All right, and now we have a change. As we can see, since A is not multiplied by anything, then it's going to be minus x. But you have to watch out at that point. Is it possible to put positive x instead of negative x? It depends on the type of the questions. So let's complete and read the question again. The question says, as we put all of these guys in a container in a 1 liter, keep in mind it's really important the volume in here, okay? The reaction is allowed to reach the equilibrium. At equilibrium, the number of moles of B is 18.32. So you can notice that B, which is a reactant, it started with 10.11 and now it becomes 18.32. So what does it mean? We just noticed that there is increase in the reactant concentration. And at that point, since you have increase, it means that the reaction is shifting backward or to the reverse direction. At that point, I have to say, instead of saying negative x, I have to say, no, it's going to be positive x for reactants and negative x for products. Okay, so I have to erase the stuff in here and complete it again. Instead of writing negative x, it's going to be positive x. And for B, since it's multiplied by 2, the coefficient for sure is 2, it's going to be positive 2x. And for C, it's going to be negative. Since C has a coefficient of 3, then it's going to be negative 3x. Okay, since we have rise, R, I, C, equilibrium, we have to add x to this magnitude to this one here, and subtract this, as we can see. Now I have to say the answer is going to be 9.22 plus x. Okay, for B, it's going to be 10.11 plus 2x. And for this guy, it's going to be 27.83 minus 3x. Perfect. In order to calculate the values at equilibrium, I need a value in here. I need a value here and a value in here. I need to determine the value of x. So how can I do it? All right. Is there any piece of information that tells me about the value of x? Yeah, sure. Let's be. The rule says we started with 10.11 of b, okay? And now after adding 2x, the concentration or the number of moles become 18.32. Okay, if we apply some math by negative 0.11, negative 10.11, negative 10.11, okay, and we cancel these guys, it becomes 2x equals to 8.21. You divide by 2, divide by 2, then the value of x is equal to 4.105. All right, so I determine the value of x, I cancel the other guys in here. Okay, if you substitute the value of x in here, okay, then the answer is going to be 15.515. You know how to substitute it. You're going to say 27.83 minus 3 times the value of x, which is 4.105. Okay, that's very simple one. Let's complete the guy in here. For sure, the value of b is given to us, which is 18.32. I don't need to do any changes in it. And so here we have 9.22 plus 4.105. The answer is equal to 13.30. Okay, we didn't finish. The question is asking me to calculate the value of Kc. The value of Kc is equal to concentrations, right? And you just notice that the concentration represents number of moles over volume. Since the volume actually is 1, you can see, so we're going to use the same number of moles without any changing. The expression of Kc is equal to products of reactants. You can see we have value of C, okay, to the power 3 over the concentration of B, which is to the power 2 times the concentration of A, which is to the power 1. And then we substitute the values as we can see. So it's going to be 15.515 to the power 3 over the concentration of B, which is 18.32 to the power 2, and multiplied by the concentration of A, which is 13.33. And at the end, the answer is equal to 0.832. And you can just make sense a little bit. Since the value of Kc is less than 1 at that point, we can just notice that the reactants at that point at equilibrium are more favored than the product.